Hi everyone, my name is Bruno Fruchard. I am a postdoctoral researcher at the SIGCHI lab in Zurich University. Today I'm pleased to present to you on behalf of my co-authors the paper called Squish, Force Input on Soft Surfaces for Visual Targeting Tasks. Advances in sensing technologies enable to augment various types of materials. For instance, smart textile enables touch interactions, but also twisting, bending, or shearing gestures. Similarly, by augmenting the skin, one can leverage natural landmarks, its inherent softness, and also deformability. Boehm and Troiano recently reviewed the literature of such deformable UIs and demonstrated how they keep evolving and creating novel devices and ways to interact with deformable materials. While previous work proposed competing devices, it rarely focused on answering how does deformability affect interaction and performance. To answer this question, we focus on force inputs. Why such inputs? First, soft surfaces deform under the pressure of the user's finger, which provides additional sensory cues by stimulating tactile and kinesthetic receptors. One can therefore assume these additional cues have an effect on user performance. Second, force input is a common focus of HCI studies. It is a accompanying alternative or complement to conventional touch interactions by leveraging one-finger interactions on small surfaces. To date, however, it remains to be evaluated on soft surfaces. In summary, we address the following question in our work. How does surface compliance affect force input performance? To answer this question, we ran a user study involving 24 participants. This study focused on a conventional visual targeting task and involved three independent variables: the surface compliance, the size of the target, and the target force level. To control the surface compliance, we cast 3 silicon samples with approximative Young's model. We chose these measures empirically as they felt equally distant in the perceptual space. To sense the pressure applied on a surface, we used a force sensing resistor, or FSR, with a 5 mm diameter that we placed above the surface and below the user's finger, as you can see on the picture. As these devices are sensitive to deformations, we evaluated its response curve by plotting its output in function of weight applied on it for each surface. We then used the depicted models to linearize the output of the sensor during our study and used a linear visual mapping. The targeting task was the following. The user could control the slider by applying more or less pressure on the surface. That task was to place the slider at the correct position of a scale to select a target force level. We calibrated the force range for each user to normalize the output. We highlighted the target force levels at each trial. The user could balance precisely the force applied on the surface to reach the level. To select it, they had to release their finger quickly, as proposed by Karsten and colleagues. Here are our results. First, we focused on the user accuracy. We calculate the accuracy as the number of times the participant could select a level correctly. For this metric, we do not find evidence of a difference between surfaces. Looking at the selection times, we found evidence of a difference for the soft surface. Selections on soft surface were slower. To look more closely at this, we studied the number of crossings in function of the target force level. A crossing corresponds to the user entering and leaving the bound of a target force level. While the number of crossings remained comparable across surfaces for low force levels, we observe differences in high force levels on soft surfaces. We therefore conclude targeting force levels on soft surfaces is more demanding in high force levels. Finally, we compared our results to the literature in rigid surfaces. We observed that for comparable force ranges, our results show an accuracy of 95% for 20 force levels compared to 89% for 10 levels reported in the literature. We conclude that force input was underestimated so far. In summary, we compared force input performance for targeting tasks on surfaces with various levels of compliance. We found that the deformability of the surface has little impact on the targeting accuracy. However, selecting targets on soft surfaces is more challenging. While we compensated for the different response curves of the sensor on various surfaces, our results showed that adapting the visual mapping for each is crucial. Finally, we compared our results to previous studies on force input on rigid surfaces and observed that force input was underestimated so far. Thank you for listening.